We are the goof for physics. We are about to present two problems that we choose and how we solve it. For the first problem, Princess Toadstool stands on the edge of 30-meter high cliff. She throws Bowser upwards at 20 meters per second. If Bowser falls all the way to the bottom of the cliff, find A. his velocity when he hits the ground, and B. the time it takes to hit the ground. For this problem, Nino Manalo and John Inigo Alves will solve for it.
Given task to me is number 1. Princess Toadstool stands on the stage of a 30-meter high cliff and she throws Bowser upwards at 20 meters per second. If Bowser falls to the bottom of the cliff, find his velocity when he hits the ground. Given VE equals 20 meters per second, acceleration equals negative 9.8 meters per second, distance equals negative 30.0 meter. Formula: V equals VE squared plus 2AD. Solution: square root of 20 meters per second squared plus 2 times negative 9.8 times negative 13.0. 20 meters per second squared equals 400 and negative 9.8 times negative 30.0 equals 294. 2 times 294 equals 588 and 400 plus 588 equals square root of 988, and the answer is negative 31 meter per seconds.
B. Given initial velocity is equals to 20 meters per second. Final velocity is equals to negative 31.5 meters per second. Unknown. The time it takes to hit the ground. Formula: final velocity is equals to initial velocity plus gt. Solution: final velocity is equals to initial velocity plus gt will be derived to time equals final velocity minus initial velocity over g. Substituting the given values, that t is equals to negative 31.4 meters per second minus 20 meters per second over negative 9.8 meters per second squared. So, following the signs of the rule of signs, negative 31.4 meters per second minus 20 meters per second will be negative 51.4 meters per second. So, time is equals to negative 51.4 meters per second over negative 9.8 meters per second squared, and the answer will be time is equals to 5.24 seconds. The answer, 5.24 seconds, is the time it takes to hit the ground. For our second problem, an arrow is shot straight up from a height of 1.50 meters with an initial speed of 45 meters per second. A. How long before the arrow reaches its maximum height? B. What is the maximum height the arrow reaches? C. What is the velocity of the arrow when it returns to the point where it was launched? And D. How long after the launch before the arrow returns to its original height? For this problem, E.J. Chua, Saison Marasigan, and Dion Pagkaliwagan will solve for this.
To solve the question of letter of problem number 4, how long before the arrow reaches its maximum height, we should need to use the given values of initial velocity, which is 45 meters per second, the value of g, which is equal to 9.8 meter per second squared, and the launch angle, which is 90 degrees. The projectile is launched straight up. Afterwards, we will use the formula to solve the time it takes for the projectile to reach its maximum height, which is initial velocity times sin theta divided by g. Then we should need to substitute the given value of the initial velocity, the launch angle, and the value of g. After that, we use the operation and solve for unknown. As a result, the time it takes for arrow to reach its maximum height is 4.59 seconds.
Number 4. An arrow is shot straight up from a height of 1.50 meters with an initial speed of 45 meter per second. Letter B. What is the maximum height the arrow reaches? The givens are initial velocity equals 45 meters per second and the launch angle theta equals 90 degrees because it was launched upwards, and the value of g equals 9.8 meters per second per squared. To answer the question of letter B of number 4, we would need to use the given values of initial velocity, which is 45 meters per second, the launch angle, which is 90 degrees as the projectile is launched straight up, the value of g, which is equal to 9 meters per second squared, and the initial height, which is 1.50 meters. Afterwards, we will use the formula to get maximum height, which is v squared times sin squared theta divided by 2 times g. Then we would need to substitute the given values of the initial velocity, the launch angle, and the value of g. After that, we use the operations and solve for the maximum height, which is equal to 103.3 meters, but it is not yet the exact maximum height as we need to add the initial height to it. Adding 1.50 meters to 103.3 meters would equal to 104.80 meters. As such, the maximum height the arrow reaches is 104.8 meters.
Problem number 4, question letter C. What is the velocity of the arrow when it returns to its original height? The given values to be used are the value of g, which is equal to 9.8 meters per second squared, the value of t, or time, which was solved in question letter A, which is equal to 4.59 seconds, and the value to be used for the initial velocity is 0 meters per second, as the projectile has already reached the apex of its vertical trajectory and is now falling back down. We will use these given values to solve for the velocity of the arrow when it reaches its original height. The formula we will use to solve for the unknown would be Vf equals initial velocity plus g times t. To solve for the velocity of the projectile, we would first substitute the given values and afterwards apply the necessary operation. The final velocity would be 44.98 meters per second or 45 meters per second when rounded off. Problem number 4, question letter D. How long after launch before the arrow returns to its original height? The given values to be used are the values of g, which is equal to 9.8 meters per second square, the values for initial velocity, which is 45 meters per second, the launch angle, which is 90 degrees as the arrow is launched straight up. We will use the formula to get the time of flight, which is 2 times initial velocity times sin theta divided by g. Then, we would substitute the given values of the initial velocity, the launch angle, and the values of g. After that, we apply the necessary operations and solve for the time of flight. The time before the arrow returns to its original height after launch is 9.18 seconds.
This is the end of our presentation. Thank you for watching.